Okay, let's start. Let's start by summarizing. This is where we're at. We're learning about different kinds of series. What is a series again? Where you sum up the terms of the list of a sequence. So we're learning about different kinds of series, and we're starting to see more and more different kinds. And we have this growing toolbox of things that we use to analyze these. And the most common question is, does the series converge or diverge? If it converges, that means the sum of all infinitely many terms sums up to a finite real number. Anything else we call divergent. So if it sums up, just gets large without bound as it keeps summing, or it gets large negative without bound, that's divergent. Or if the sum is just jumping but not honing in on a particular real value, that's also divergent. So a convergent series means the sum of all infinitely many terms is a finite real value. That's our predominant question here when we look at these series. So in our toolbox, the first thing we have is the divergence test. And we say that in order for the series to have a chance to add all those terms to add up to a finite value, what has to be true? What's necessary? What has to be true? You got to know this. If you don't know this, all this other hard, complicated stuff that we do for the next couple of weeks is for naught, for nothing. What has to be true for you to get an infinite number of terms to sum together to a finite value? Sequence has to do what? It has to go to 0. The sequence, the limit of the sequence must go to 0. What if the limit of the sequence goes to a non-zero value, but the limit of the sequence does exist? The series will diverge, and you have to know why. You should have a mental image of what's happening when a sequence approaches, the list approaches a finite value, and now you're going to add all those together. Of course, that sum can't possibly converge. You have to have a mental image of that and be able to explain it on the exam. Okay? So this is the divergence test. If the sequence, the list, approaches a non-zero number or doesn't have a limit at all, the series can't converge. That's the divergence test. So the flip side is the necessary condition for a series to converge is that that sequence approaches 0. Now, does that guarantee that the series will converge? No. Some series whose sequence goes to 0 will converge, and some won't. Okay, so that's divergence test. Next thing we had was, let's talk about geometric series. This is a very specific type of series that looks like this. Here was the form we've used most often. A r to the n minus 1. Okay, that series converges so if that sequence goes to 0, then the series converges for a geometric series. If that sequence goes to 0, and how does that sequence go to 0? Right, so this converges if negative 1 is r is between negative 1 and 1. And that relates back to when we were talking about sequences, and we talked about what? P to the n. So it's very similar, right? P to the n is very similar to r to the n minus 1. It's the same kind of idea. And p to the n goes to 0 if p is between negative 1 and 1. That's what we said for sequences. So now this is kind of the series version of this sequence. P to the n is a geometric series, but you can have a coefficient a. And now p has become r. Now P is like R. And so in this case, as long as that sequence converges to 0, P to the n goes to 0, then the series converges. And what does it converge to? Right, we showed in class a couple of classes ago that that sum is A over 1 minus R. And then we also showed the alternate form to that. We shifted the index. If n equals 0, then to get the same exact terms, it would be A R to the n. And if you're not sure, just start writing out what the terms look like. The terms of this one, starting at n equals 0, should be the exact same terms. And they are, okay? And they are. You get the exact same terms. So when the very first term here is A R to the 0. The very first term up there is A R to the 0. Then the second term is A R to the 1. Second term up there, A R to the 1. So you get the same terms added together. Okay, what else do we have here? We had something called the P series. So the notation that the math world has used is kind of confusing because when we talked about sequences, we used P to be this P to the n. But now when we talk about a P series, that's not, it's different than this P to the n thing that we talked about for sequence. So be aware of that. So let me write it in red. A P series is this form. 1 over n to the P. So if we were making up our own notation, we wouldn't have done it this way. This is confusing, right? So you gotta file this, you gotta work on filing this correctly. First, we call the P to the n sequence, P was the base. And then P kind of became R for a geometric series. Those are kind of, that's kind of the series for this P to the n sequence. But now what we call a P series is where P is the exponent. So you gotta file this. You gotta make sure you have these P's straight, okay? And we said this converges when what? When P is greater than 1. When P is 1, what do we have? When P equals 1, what do we have? The harmonic series. That's an important series. The harmonic series, just 1 over n. 1 over n is the harmonic series. Okay? Does the harmonic sequence approach 0? Does the harmonic sequence approach 0? 1 over n. Does the harmonic series converge? No, right? It does not. We showed that. We proved that it gets just, the sum just keeps increasing, right? We showed that it just keeps increasing. But as long as that, if you have 1 over n to any power greater than 1, 1.01 or 1.00001, that will converge, all right? So as long as that P is greater than 1, you get a convergent series, all right? And then we have the comparison test. Was another tool we have. I'm not going to write it out again, but we'll just mention it here. The comparison test is when you can compare your given series. You're analyzing a given series. You can compare the terms of your series to the terms of another series that you know either converges or diverges. So if you're trying to, if you have a series and there's another series, I don't want, anyway. Let me just show the comparison test again here. Don't write it down again. We're trying to show that the given series sum of a to the n is divergent. Then we need another series that diverges, and every term of ours has to be greater than every term of the one we know already diverges. It should make sense, right? It should make sense. You've got a divergence. You know of a divergent series. You're analyzing a series such that every term of yours is greater than the divergence series. So yours is going to diverge too. Okay? Convergent, likewise, but it's flipped now. You know of a series that converges, and all the terms of the series you're analyzing are less than the terms of the one you know converges, then yours is going to converge too. Should make sense. Should make sense. Because the sum of yours will be less. For the first one, the sum of yours will be greater than one that you know is already divergent. So this is the idea of the comparison test. Okay, so that's our, have I forgotten anything from our toolbox? I don't think so. We mentioned it, but it's not really in our toolbox. Okay. Okay, so let's look at, now that we've kind of reviewed those, let's look at a couple of Weber problems. First one is number 1. Here. Okay, number 1. So when I look at number 1, it would sure be nice to write it in a form we can kind of make maybe a little more sense of here. So I'm looking at the sequence and trying to figure out what formula is going to get me this sequence. So when n is 1, I get negative 6/9. When n is 2, I get positive 36/81, etc. So what formula using n will generate the terms of the sequence? So it looks like this is just the first term squared, right? And then is this the first term cubed? So that basically the power, you basically have negative 6/9 to the n. And how can we test it? Well, let n be 1. See if you get the first term. Let n be 2. See if you get the second term. And you will. Okay? And n starts at what here? 1. So what do we have? Do we have, first of all, so we can use the idea of the divergence test first. Does the sequence converge to 0? Does the sequence converge to 0? Negative 6/9 to the n. Does that sequence converge to 0? That sequence is like p to the n. When does p to the n converge? The sequence. Between negative 1 and 1. When is our p-value between negative 1 and 1?
Yes.
Yes, we have a sequence here that converges to 0. So this has a chance to converge. Next thing we look at is, okay, so remember, if our p to the n sequence is really the same as geometric, right? This is really a r to the n minus 1, somehow. Is it going to converge, the series? Yes, geometric series that have a p or r value between negative 1 and 1, they converge. They always converge. This is going to be a convergent series. So now we need to figure it out, and we have that formula that we derived to get the sum. But we just need to get it in the form a r to the n minus 1. Right now it's just like r to the n. So we need it to be in the form something a times something to the n minus 1. Okay, so you have to have a mental image of what an exponent means, especially as things get harder. What does that mean? It means take negative 6 to the 6/9 and do what? Multiply it together n times. So you've got to imagine that. Or if you can't, write it out. Negative 6/9 multiplied together n number of times. So what about negative 6/9 to the n minus 1? Well, I had n of them. Now how many of them do I have? Compared to n of them? One less, right? I have n minus 1. So before I had negative 6/9, I had n of those multiplied together. Now I have one less. But I'm trying to keep these equal. So I need this to be equal to this, but in the form AR to the n minus 1. So to make these equal, I still need n of them. But this part is one less. So how am I going to have n negative 6/9 multiplied together in this expression? I need one more. I need one more. And so that's what the a will end up being. So now I have one less, but then I multiply by one more, so I'm back to my original n of them. N negative 6/9 multiplied together. And now it's of the form AR to the n minus 1, geometric. Okay? And so now I can say that that series converges to or equals a over 1 minus r, negative 6/9. Remember in web work, you can always put in expressions. Negative 6/9 divided by 1 minus negative 6/9. A over 1 minus r. It will be your calculator if you let it. A over 1 minus r. Questions on that one? Okay, the next one also poses some difficulty. So I have cosine 0.7 to the k. K equals 1. What kind of series is it?
Is it just like the previous one?
He said just like the previous one, meaning it's geometric. Is it geometric? Yeah, it's a number. Cosine 0.7 is just a number. It's just an expression for a value. Cosine 0.7 is a value. You have a value to the k. So when does this converge or not? We're going to check what? Is cosine 0.7 between negative 1 and 1? Now this is radians, not degrees. 0.7 radians. Okay, that's radians. Make sure your calculator is set. So if we're going to check it, what is cosine of 0.7 radians? As soon as you get it, shout it out.
0.7648422.
Okay, inappropriate number of decimal places. 0.765. Okay. Okay, so it's about 0.765. Convergent geometric series or divergent? Convergent is between 0, it's less than 1. It's less than 1. And so in this actually we're going to end up doing the same thing. We're going to rewrite it in our form. And when we rewrite it in our form, I just made one less, cosine 0.7 multiplied together. I had k of them multiplied together. But what I just wrote is one less of those multiplied together. But I need k of them to keep it equal. I need this to be k cosine 0.7s multiplied together. So I'm going to need that one more. So it's going to be a over 1 minus r. A over 1 minus r. Questions? Okay, there was one more towards the end. We'll talk about this one. Oh, comparison. So for this, what might we be comparing? So it says use the comparison test. So we look at this and we see this, look, n to the 9th in the denominator. So that's kind of like 1 over n to the 9th. Can we compare this to 1 over n to the 9th? So we got to be familiar with sign. Sign of n always stays between, sign of a number always stays between what and what? Negative 1 and 1. So sign squared of n is always going to stay between 0 and 1. So the range of sign is from negative 1 to 1. And if you square everything, now you're going to make everything positive. but it's still going to only go from 0 to 1. You can't square anything less than 1 and get something greater than 1. So what's going to be true about every term, sine squared n over n to the ninth? If this is between 0 and 1, how is it going to compare to 1 over n to the ninth? If your numerator is between 0 and 1, then you're always taking a fraction of 1 over n to the ninth. Do you see that? This number is always between 0 and 1, then how does this first fraction compare to the second? It's got to be less than or equal to. It has to be. Because you're always taking a fraction. The biggest thing you're doing is maybe multiplying it by 1. But otherwise, you're taking a fraction of 1 over n to the ninth because it's between 0 and 1. And so every term of, and this is true for every n. That statement's true for every n. Okay, so, and what do we know about 1 over n to the series 1 over n to the ninth? Convergent or divergent? Convergent p series, because 9 is greater than 1. That's our convergent p series, 1 over n to the p. And so now what? Our series has all terms that are less than or equal to the terms of a convergent series. Conclusion? By comparison, convergent. The one we're analyzing, every term of the one we're analyzing is less than or equal to the terms of a series that converges. Should make sense now. So our sum is going to be less than the sum of 1 over n to the ninth. And if it's less than a convergent series, it's convergent. What about if your series is greater than a convergent series? What's the conclusion? What about if the series you're looking at is greater than a convergent series? No conclusion. It still might be convergent or it might be divergent. But if your series is less than a convergent series, which we can show because every term is less than or equal to, then your series converges. Okay, let's go on to new stuff. So that's kind of a review. We got the toolbox. We're going to add to the toolbox here. Okay, so an alternating series. We've already seen examples of alternating series, but let's define it. So an alternating series is of this form. Now, as we progress, we're going to see lots of series that now start at n equals 0. The reason why we started at n equals 1 before is because we were thinking of a transition from sequences. And sequences make sense to have that first term be 1, 2, 3, 4. But now as we're looking at a lot of series, we're going to see lots of series that start at n equals 0. Okay, so n equals 0. What does alternate mean? Alternate sign, positive, negative. So this is the form of an alternating series. So I want you to write out. You see this, you think what? See this, what do you think? Write it out. What does this mean? Mathematically, what does all that notation mean? Write it out. What's the first term? B0. Second term? Minus b to the first. Third term? Not b to the first. B1. This is subscript. B plus B2. Then minus B3, etc. Now the negative 1 to the n is what's doing the alternating for us. So the Bn sequence is actually a positive sequence. All the terms of the Bn sequence are greater than or equal to 0. The negative one, so we've got it in this form, so we're forcing the negative 1 to the n is doing the alternating for us. Okay? It's alternating on this positive sequence. Okay, so alternating series test. So we'll just write it just for clarity. If Bn is greater than 0 for all n, the series is convergent if the first condition is that sequence Bn is a decreasing sequence. A decreasing sequence. That means that every next term of the sequence is less than or equal to the previous. For all n, the other criteria that you need is that the sequence converges to 0. So what's going on here? When we talked about, every time we've talked about series up till now, we said if the sequence approaches 0, does the series converge or not? Maybe. Depends on the series. Maybe it does. That's the necessary condition, but it's not sufficient. But with an alternating series, if your sequence goes to 0, if the Bn sequence goes to 0 and it alternates, then the series converges. So this is enough now. So if you have an alternating series, if your sequence without the alternating goes to 0, then that does it. Okay? So what's going on with that? So let's look at an example. What about okay? So here's what do we call this? This is the alternating what kind of series? The alternating harmonic. The alternating harmonic series because it's the harmonic series 1 over n, but instead of adding all of them together, it alternates. What's the first term? Well, let's see here. Let's do n. So sorry. Let's do n to the n minus 1. So using n minus 1 versus n just swaps which terms are negative and positive, right? So if you do negative 1 to the n minus 1, you just took all the ones that were negative before when you had negative 1 to the n, made them positive, and vice versa. So it just swaps negative for positive, okay? So this is the alternating harmonic series. What's the first term? Everybody, what's the first term? Second term? Negative 1/2. Third term? Keep going. It keeps going like that, okay? So before, we know the harmonic series diverges. But if it alternates, then it converges. Why? Why? What is it about alternating now that makes the harmonic series converge? It should. That's not a hard question. Yes, sir. But okay, yeah. So you're on the right track. But why is it if we add all those up positively, it diverges? But now if we alternate signs, it's going to converge. Yeah. Yeah. So it's not. Every other term is getting subtracted now. So this is why it will actually converge. So let's actually draw this out. Say we start at 0, and when we add the first term, where are we after we have the first term? We're at 1, right? So after the first term, we're at 1. And then now we add the second term. Where will we be at now? So we'll be at 1, and then we're going to subtract 1/2. Where will we be now? We'll be back at 1/2, right? And then we're going to add a third. Where's that going to put us? Right here. When we add a third, that's going to put us at 5/6. Right? So that puts us at 5/6. And now we're going to subtract a fourth. Are we going to get back to 1/2? Not quite. I don't know what 5/6 minus a fourth is on the top of my head. Anybody? 12th. 2/12 minus 3/12. No? Yeah, 2/12. Where am I going wrong here? What is it? What is it? Oh, 7/5? 7/12. Couldn't do the math fast. Okay, so what's happening? Every time we're going to add or subtract a smaller number than what we did before, so it's just going to keep oscillating like this, but it's going to get trapped in here, right? And so as we keep adding a term, we're going to be honing in on a finite value. Every other term gets subtracted instead of added. So now it's going to, that sum is going to approach a finite value instead of just adding this way, right?
Is there a way we can find out what that value is?
Yes, but that's not our goal today. But yes, there are techniques. Yes. Okay, so then let's talk about something called absolute convergence. What does it mean for a series to be absolutely convergent? I mean, it's absolutely convergent if so I should have said a series so a series sum of a sequence AN is absolutely convergent if if you were to take the absolute value of every single term of the original series and add those up, if that series is convergent, then it's absolutely convergent. What we just saw in the example was when you have an alternating series, that alternating effect helps it to converge, right? Because half the terms are negative and half are positive. That's going to help keep the value to a finite value. So this is kind of like a stronger sense of convergence, all right, is that if you were to take the absolute value of every term and it's still convergent, that's what we call absolutely convergent. Meaning what? It doesn't need the alternating effect to help it. It doesn't need an alternating effect to help it. So without the alternating effect, it still converges. So is the alternating harmonic series absolutely convergent? Is the alternating series absolutely convergent? Well, that's asking the question. So then you're analyzing this. You're analyzing this series, which is essentially, what series is that? You take the absolute value of all those terms and add those up, it's the same as what series?
Harmonic.
The harmonic series. So is the alternating harmonic series absolutely convergent?
No.
No, because if you take away the alternating effect, if you make all the terms positive, you get the harmonic series, which we know is divergent. So this is then what's called conditionally convergent. It's conditioned on having the alternating effect. The alternating harmonic series is conditionally convergent. All right, so what about new example?
So we switch from harmonic to a P series.
Okay, so harmonic is a P series. Harmonic is a P series. So this one, absolutely convergent, conditionally convergent, or divergent. So this is the new way we'll be analyzing a lot of series. Is we'll say, is it absolutely convergent? Is it conditionally convergent? Or is it divergent, not convergent? So of those three, which would you say it is? So we can use this. So we're going to investigate this. Take all those terms and make them positive. Or just take the absolute value of those terms. And what do you get? Just 1 over n cubed. That should be a 3. So, absolutely convergent, conditionally convergent, or divergent? The original series over there to the left. What do you think? So what about this? 1 over n cubed. Convergent or divergent? I hear some people saying divergent. This is a convergent P series. P is greater than 1. P is greater than 1. P is 3. This is convergent. This is convergent. Therefore, the original one is absolutely convergent. It doesn't need the alternating effect to help it. Even without the alternating effect, it will converge. Now, is the sum the same? Is the sum of this one the same as the sum of this one? Clearly, one is greater. Which one is greater, left or right? The one on the right is clearly greater. It's all positive terms. Over there, you're subtracting off half the terms. You're going to get a different sum, but they're both going to converge, and then that indicates that our original one is absolutely convergent. Okay, questions on that idea? Absolute convergence. So thus, original series is absolutely convergent. Anybody have a question? Okay, so there's a test called the ratio test. The ratio test tests for absolute convergence of a series. We're going to look at the limit of this sequence. What is the sequence? You're going to take a term of this, any term of the sequence, and the next term, and form this ratio of the next term to the current term, and look at that sequence. That's you're making a new sequence, and you're going to look at that sequence, and you're going to investigate the limit of that sequence, the absolute value of that sequence, as n goes to infinity. So let's call that limit L, okay? So then you're going to examine the limit of that sequence. If L is less than 1, then the original series is absolutely convergent. So today we're going to state this test. We're going to do a couple examples, and then Friday we're going to kind of dig a little bit more into this, what it's about, why this, what's happening, okay? What's happening. Today we're just going to state it and do an example. If L is greater than 1, the original series diverges, okay? If L is equal to 1, the test is inconclusive. Got to do something else. Okay, so we're taking that series. We're going to make a positive sequence out of that series by taking the current term and the next term generically, making a ratio, and taking the absolute value and looking at the limit of that sequence. And then here's how we test that sequence and conclude about the original series. So let's do an example. Okay, negative 3 to the n over n cubed. So the ratio test would be to look at that sequence, right? So what is a to the n? A to the n is simply, that's the a to the n, that's the a to n term of the sequence. And so then what is the next term of the sequence? A n plus 1. Well, it'd be negative 3 to the n plus 1 over n plus 1 cubed. Okay, and we're going to look at that ratio. We're going to simplify that ratio and take the absolute value of it, and then the limit as n gets very large. Okay, so the technique here is kind of to gather things together, and then also you can, because you're often your an sequence is a ratio itself, you can start by flipping and multiplying. So you can actually start this process here if we wanted. So we could do it this way, and it's helpful. So instead of thinking of it as an plus 1 over an, just start by an plus 1 times the reciprocal. It just helps to organize it a little better. So I could have written this first. I could have just started right with that step right there. An plus 1 times 1 over an, which is the reciprocal. And then we kind of gather like things together here. We say, what's negative 3 to the n plus 1 over negative 3 to the n? So here I have n plus 1 negative 3's multiplied together, and here I have n negative 3's multiplied together. If I were to divide, what would I be left with? 1 negative 3 in the numerator, right? There's one more negative 3 in this product than there is in this product. That's the kind of imagery you should have about exponents, right? There's one more negative 3 in this product than there is in this. So if I divide, I'm going to be left with 1 negative 3 in the top. And then I'm going to have n cubed over n plus 1 cubed. So as n gets really, really large, what's the limit of n cubed over quantity n plus 1 cubed? We should know that. What's that limit of that sequence? Gets very close to 1. If you multiply out the bottom, you'd get your leading term would be n cubed. And so then you'd be looking at n cubed over n cubed for large n. That's just 1. So what's this limit? So as n gets big, that goes to 1. And then we have absolute value of negative 3. 3. Okay? Conclusion about this initial series. According to the ratio test. Divergent, because this is greater than 1. Because that limit is greater than 1, conclusion is that our original series that we looked at is divergent. Okay? Notice, it's alternating. But even the alternating can't save this one, right? So even the fact that original one alternates can't save it. It's still that one's still gonna diverge according to the divergence test.